Hey yo, what's up everyone? It's your boy JOHABRAHAM. And we're back with the biochemical kinetics. Cause I got a new assignment coming up, a lot of shit. And this is a new setup. I don't know if you could notice it because you could see the background. Like lights from the background, it's coming in pretty powerful. Oh, yeah. Why did I do this? I don't know. I just felt like I need to change the setup. Don't ask me. I just changed it. I just did what I want. Okay, don't ask me. So right now my windows are behind me. So sunlight is coming from the behind and my setup is facing the sunlight. Usually it was my face that faces the sunlight, but now it's my monitor screen that's facing the sunlight. It's okay. So let me pull up the assignment. It's been 2 days, huh? Make sure you set a timer for 1 hour. Two days. Two days. Exercise 12. Number 12. Sequence analysis. No, Biochemical Kinetics Exercise 11. New folder. EXC 12. Oh. Yep. Okay, I downloaded it. Downloads. Pick it up. Save to the file. Oh, come on. That's all you gotta do. You just have to save to the file. You couldn't do that. So this is electrochemistry redox equilibria. And not like the last time, we gotta submit all the questions. We gotta do all the questions. It's not that hard. Come on. It ain't never hard. Fícaro, Fícaro, Fícaro. Bing, bing, bing. Calculate the standard potential of the half cell AU3 plus, AU3 plus, AU plus using redox potentials E0. A lot of shit to know. This is the first question from my, this is the first question from what? First question. From my biochemical assignment 12. I need my music. Where my music at? Where my music at? Oh, dude, yesterday's rain was so bad. My bag is wet. It is wet with the dirt. Not rain. It was just snow or water on the road. Fucking hell. This guy goes here. I'll clean it later. Where's my tablet at? My holy Bible. Jo, genau. Okay, if I have the tablet, the big boy is gonna go keyboard. Just gotta sit this one out. Now we are given two standard production potentials versus she. I'm guessing that is standard hydrogen electrode or standard hydrogen cell. So she like that. What's downloads? Why is it downloads? Just go to the whole music page. Come on. Why is shortcuts not working? Okay, let me try this on Safari. Oh, come on. The automation should work. Guess it don't. Guess it did not. Stupid. I gotta use my second phone just for this part. I gotta say, the older 7 Plus, the automation works on the older phone. What is that? What does that mean? What kind of stupid stuff is going on? How do I do this? Okay. What what happened to the automation? Oh, come on. I apologize, people. Just a minute. It's not even working. Oh, come on. Oh, is it the save? Okay, battery save. Maybe that's the problem. Okay. It was the like low power mode. This is pure electrochemistry. Look, bookkeeping problem. No kinetics, no biochem tricks. What do you mean? We were given two standard reduction potentials versus SHE, standard hydrogen electrode, I guess. And asked to find the standard potential of half cell AU3 plus AU plus. This is pure, okay? Write down what is given. Standard potentials are always written for reduction reactions. Reduction. Gain of electrons. Uh-huh. And the second one, AU plus AU. Uh-huh. What we want, AU3 plus AU. That's already given, right? Okay, no. AU3, okay, that's the half cell. Okay. Key rule you must remember, important. Standard potentials are not additive. You cannot just subtract voltages directly. Instead, you must work via Gibbs free energy. Delta G0 equals minus N Fe. This is non-negotiable in electrochemistry. Convert known potentials into delta G. Use delta G is equal to minus N Fe. Reaction 1, AU3 plus to AU. That's a 1.42. And AU plus 2, okay, well, that's blah, 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 blah. What is this N? Is this the number of electrons? Okay, I'm having some doubts. Could you explain more on the half cell? And also what? The half, wait, I asked the half cell. It's not seal, it's cell. And more on the SHE. Also, could you also explain the terms involved in this Gibbs? Is it Gibbs free energy? Yeah. What is half cell? Half cell describes one redox couple, meaning one chemical species, two oxidation states exchanging electrons. One chemical species, two oxidation states exchanging electrons. General form, oxidized form, reduced form. Examples. This problem. What does AU3 plus AU plus mean physically? It represents the equilibrium where AU3 plus gains two electrons to form AU plus. Both are cations, and one is smaller compared to this one. So this half cell tells you how strongly AU3 plus wants electrons, how stable AU plus is after reduction. How stable AU plus is after reduction. How stable AU plus is after reduction. How much electrical work this redox step can do. The half cell potential is not measured by itself, it only has a meaning relative to another half cell. That brings us to SHE. Standard hydrogen electrode, I knew it. I knew it. Standard hydrogen electrode, SHE, SHE is an arbitrary reference electrode chosen so that everyone in the world uses the same 0 point definition, 2H plus 2E minus. Uh-huh. So, so standard conditions, 1 mole per liter H plus, 1 bar of H2 gas. Okay, why do we need She? Because absolute electrode potential cannot be measured. Only difference in potential can be measured. So we say this half cell has E0 equals 1.42 volt relative to SHE. It is 1.42 volts more favorable for reduction than hydrogen. Uh-huh, uh-huh, uh-huh. What does standard reduction potential actually mean? The standard reduction potential means answers one question. How favorable is it for this species to gain electron under standard condition? How favorable is this species to gain electrons under standard conditions? Sign interpretation, more positive E0, strong oxidizing agent, more negative E0, stronger reducing agent. This means Au plus really wants electrons. It will easily get reduced compared to H plus. Why Gibbs free energy is involved? This is a core idea. Electrochemistry is just thermodynamics in disguise. Stop yapping. Electrical work equals chemical free energy. That link is G0. This equation connects chemistry, electricity, and thermodynamics. Meaning of every term here. Standard free energy change. Maximum useful work obtainable from this reaction, units, joules per mole. Interpretation, spontaneous, non-spontaneous. Number of electrons transferred. Uh-huh. So for standard hydrogen electrode, it's gonna be 2. Uh-huh. This matters because more electrons, more charge moved, more work. More work, more work done, or more work need to be put in. My mind is still loading after the 2 days gap. No song. Looks like that's the potential this thing. That's the best this thing can do. Oh, this guy's so slow. Not even trying. Not even trying. Break down, break down, break down. Kanishimade, break down, break down. Kanishimade, break down, break down. Mm-hmm. 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 play. So here, this more work, is that the work we giving in or the work produced DUCD as part of the reaction? I should not ask that question right away. More electrons, more charge used, more work. Faraday constant, okay. Charge of 1 mole of electrons. 1 mole of electrons, interesting. What? 1 mole of electrons. That means 6 into 6.022 into 10 raised to 23. One electron, tiny charge. 1 mole of electrons, huge charge. This converts per electron to per mole of reaction. E0, standard cell or half cell potential. Electrical driving force, unit, volt equals joules per coulomb. Interpretation, how much energy you get per unit charge. Why the minus sign? Because positive E0 means the reaction releases energy. Release energy equals negative delta G. So E0, Y potential cannot be directly added. Important exam trap. Shh! There's no traps in exam. There's only those who know, those who don't know. And I gotta say, I am one of those don't know persons. Voltages are energy per charge. But reactions combine energies, not ratios. Okay. So you must convert electric potential, standard cell or half cell potential, okay. Potential to Gibbs free energy, add / subtract the Gibbs free energy, convert back to E0. That's exactly what you did for A3. One sentence summary you can memorize. Have half cell potential measures Gibbs free energy charge per mole of electrons. Half cell potential measures the Gibbs free energy charge per mole of electrons for a redox couple. Reference to the standard hydrogen electrode and must be combined via delta G 0 equals NFE because voltages themselves are not additive. Voltages themselves are not additive, okay. So the Gibbs free energies can be added, okay. If you want next Latmier's diagram, y AU plus disproportionates. How this appears in biochemistry, common exam mistakes. No. More electrons, more charge, more work. So, okay. Short answer, it is the work produced by the reaction, not the work you supply. Now, the precise reasoning, what more work means. Electrical work is given by work equals charge times potential. Charge times potential. Potential is a relative thing, right? There's no standard value for potential. Here, charge equals NF. Number of moles times Faraday constant. Number of electrons involved times Faraday constant. So maximum electrical work produced because of the minus sign. What? Is there a minus sign in the equation? Oh yeah. If E0 is greater than 0, Then it's a spontaneous cell. Electrons flow on their own. The reaction produces electrical energy. That energy can power a circuit, do mechanical work, be harvested. Energy? Energy? You say it can move stuff. In this case, delta G0 is less than zero. That meaning the system does not does work on the system does work on the surroundings. Yeah, it's less than zero. It's a spontaneous. Okay, okay. Role of more electrons and increases, then more electrons flow, more charge moves through the circuit, more energy is released at the same voltage. More energy is released at the same voltage. If there's more electrons, okay. Okay, now we're so here Au3 plus gets 3 electrons to form a stable gaseous atom, I guess. No, not gaseous atom. Or it forms normal state instead of an anion. No, cation. So when it gains that electrons, it releases electricity? Where? No. Where does it gain these electrons to form Au? Is it the solution? Is it from aqueous solution or ionic solution? I don't know. More total energy delivered. Again. This is my problem. I just keep on looking. More total energy delivered. What is not? Not work you're putting into the system, not energy required to force the reaction. That would correspond to, okay, in that case, you must apply work. Electrolysis. Okay. Okay. Could you explain this statement a bit more? So, here the Au cation gains 3 E minus to form the normal Au, and during that the transfer of electrons to the Au atom is that where the potential difference is seen? Is that where the potential difference is seen? Or am I missing something? Also, could you explain this value? Because right now my brain is not coming up with the exact explanation for those units and how the whole thing works. You're close, but one key conceptual correction is needed. What this number does not describe a single electrode by itself. The voltage cannot exist at one electrode alone. Voltage is actually always a comparison. Okay, I understand that. So this value means when half cell is connected to a standard hydrogen electrode under standard condition, the cell voltage is with gold acting as cathode. With gold acting as cathode. Anode, cathode. Not gonna lie, my brain is not coming up with the exact you know. When AU is connected to standard understanding condition, the cell voltage is with gold acting as cathode. I just read this cathode. I'm a bit confused on the term cathode. Let's look it up. Written as reduction standard convention. The reaction is very favorable. Gold 3 ions strongly want to gain electrons. Okay. Where is the potential difference actually coming from? Not during electron transfer inside the atom. That intuition is mistake. I'm thinking the movement of electrons from one place to the gold atom. Charge separation at the interface. At metal solution interface, Au 3 plus ions in the solution, 1 electrons. Au metal can supply electrons. This creates excess negative charge on the metal, excess positive charge in the solution. Excess negative charge in the metal. Yeah, metal, CF electrons, yes. Excess positive charge in the solution. That separation of charge creates an electric field, electric potential. Wait, the electric field is between the solution and metal. But you cannot pinpoint something in the solution. This is called electropotential. No wire, no current, but the tendency is already there. So now every other half cell is measured relative to this. So gold is 1.42 volts. What does 1.42 volts mean physically? 1 volt is 1 joule per coulomb. When I read these units, my brain is not coming up with what is a coulomb? What is a joule? That's when you know, yeah, I'm reaching my the brain is not braining. Each coulomb of charge transferred through this cell can release 1.42 joules of energy when paired with Chi. Since one electron, and here N is 3 electrons. During transfer of electrons to a the potential difference exists between electrons flow, I understand, due to the charge separation of the metal solution interface, and it describes how much energy is released. Okay, it's a charge separation between a metal solution interface. Okay. Mm-hmm, mm-hmm. Mm-hmm, mm-hmm, mm-hmm. My hands are getting cold. Let me heat that. Heat it up. Okay. Okay, I kinda understood the charge separation of a metal solution and the uh uh what was I thinking? So I understood the charge separation of metal solution. Metal solution what? Uh, and the resultant potential difference resultant potential difference slash field, but I'm kinda having a hard time in visualizing this. So right now I'm guessing a metal in a solution. Okay. uh, Come on. Come on. Stop. So I'm guessing, and the flow of electrons are from the solution. No, are from the metal to the solution, and that flow of electrons is what results in the PD potential difference, but there should be a point where it stops. I'm still having some not loopholes, some, I wouldn't say loopholes, I'm still having some I am a beginner to this, so I have a lot to You're thinking in the right direction, but let's slow down, visualize this properly. It's subtle because nothing is moving freely, yet you don't need a current for potential difference to exist. Picture the interface. Think of a gold metal plate dipped in a solution of gold ions. The metal has free electrons in its lattice. The solution has positive ions and solvated electrons in water. If Au ions are hungry for electrons, they pull the electrons from the metal, accumulate the metal surface. Some positively charged builds up in the solution near the surface. This is charge separation. Negative side metal surface, positive side solution layer. Okay. Even without a wire, this separation generates an electric field pointing at the solution of the metal. Huh. So I'm guessing that the electric field depends on the shape of the metal, because that metal depends, that shape of the metal decides the solution that's going to surround the metal, and that shape is where the electric field forms. So it's basically an electric field forming in the shape of the metal. Maybe that's your electrode potential. Why the electrons flow stops. It doesn't keep going forever because the electrons leave the metal, it becomes positively charged. As Au3 plus ions gain electrons, the solution becomes slightly less positive locally. The electric field now opposes further electron transfer. I'm just searching for a meaning of a word. Just a minute. Oh no. Shit. Okay. Uh, okay, come on. Get back to this. You're thinking in the right direction. Pick the interference. Some electrons accumulate on the metal surface. Okay, some positive charge builds up in the solution. Why the electron flow stops? It doesn't keep going forever because as electrons leave the metal, it becomes positively charged. Wait, electrons leave the metal becomes positively charged. As Au3 plus ion gains electrons, the solution becomes less positive locally. The electric field now opposes further electron transfer. So equilibrium is reached when the chemical push of Au3 plus 1 electrons equals. That is why no net current flows at equilibrium, but a potential difference exists. Think of tug of war between chemically driving force and electrostatic repulsion. When you connect the wire, Once you connect the wire, the electrons flow along the wire from metal to the other electrode, or vice versa. This flow is current, and potential difference now drives work, but the potential itself exists even if no current flows. uh, when you connect the wire, blah, 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 blah. Okay, when does this equilibrium reach? I'm kind of getting it, but it's over. Yeah, it's over. Ah, come on. It's not playing. What did I do to you, bro? Okay, something's happening. It should work. It did work. It's working. Connecting a wire let the spring release energy, electrons move, energy is extracted. If you want to... Okay, okay. I'm starting to get this, but could you explain again on reaching the equilibrium part where you said when so come on where you said the... What is this wanting electrons? There's the term for it. Uh, electronegativity? Yeah, electronegativity. Electronegativity of... Oh, of... My spelling is fucking AU cation and the electrostatic repulsion are equal. Also, when we connect a wire to this and connect that wire to a metal in there, in solution itself, does that result? I don't think so. Does that result? Energy just keep on flowing? I don't think so, but could you also explain this one too? no, it's about 1 hour. God damn it. It did not even start. Let's go step by step, clarify these points. Reaching equilibrium at the metal surf solution interface. Picture your gold electrode in Au3 plus solution. Okay, stop getting distracted, boy. Reaching equilibrium at the metal state solution interference. Picture your gold electrode in solution, initial state. One, the electrons, they pull some from the metal. Charge separation begins. Metal becomes slightly positive when electrons left. Solution near the surface is slightly less positive because if Au3 plus gets reduced, electrostatic repulsion builds. The positive metal surface starts resisting more electrons. Oh, wait. Positive metal surface starts resisting more electrons. Solution near the surface becomes slightly less positive because Au3 plus gets reduced. Uh-huh. The positive metal surface starts resisting more electron loss. The negatively charged electrons on the metals create an electric field opposing the flow of more electrons. Electrons. Positive metal surface starts resisting more. Like if I could draw this, I think that makes a big difference. Let me draw this. So let's say a metal that's Au and the solution Au3 plus. This has more electrons, this has less electrons. So electrons go from Au to Au3 plus, and the Au3 plus joins the metal. Okay. If you connect a wire to this electrode and another metal electrode immersed in the same solution of different solution, electrons will flow through the wire. If there is a difference electrode potential between the two metals, current flows and energy is released, which can do work, but this does not flow indefinitely. As electrons move, they reduce the potential difference across the electrodes. Once the electrodes reach the same potential, no net electron flow. Think of it like drawing a tank of water to a lower tank. The flow only happens until the water level equalizes. Electrochemistry, the water level is electrode potential. Okay. I'm trying to draw this Au3 plus and Au. Don't draw, don't make any pictures, just answer my questions. So right now Au is the metal and Au3 plus is the solution. Au has E minus in it that the Au3 plus wants. So E minus flows from the metal to the solution, and the Au ion accepts the E minus, and does it join the metal lattice, or what's gonna happen to the ion that got enough to form the metal? Electron transfer. Au3 plus ions near the surface of the metal pull electrons from the metal. Each Au3 plus gains 3 electrons and becomes a neutral atom. Where does this Au atom go? Usually it deposits onto the metal electrode. Okay, that's what I was thinking. So the solution loses Au3 plus ions, and so the solution loses Au3 plus ions, and metal grows slightly. Effect on the metal. Oh, what the fuck was that? Chasing the sun. Electrons leave the metal to reduce. The metal becomes slightly positively charged at the surface. This positively charged builds an electric field that resists the flow further electrons low. This is what happens in electroplating. The solution loses Au3 plus and metal grows slightly. Okay, okay. Now, okay, before this, okay, okay, right now, during this, how is the electric field? It's from the metal to the solution as the E minus is moving to the solution. Or is it the opposite? So the electric field is actually pointing from the positively charged metal towards the solution. Okay, now the direction of the electrons. Positively charged metal towards the solution. Huh? As the electrons leave the metal to reduce, the metal becomes positively charged at its surface. The Au3 plus ions that haven't yet gained electrons are positively charged. So there's a buildup of positive charge in the solution near the metal surface. By convention, the electric field points from positive to negative. That's a positive. So the field is from the metals towards the solution, okay? Electrons themselves move opposite to the field. So if we close this up, Au, oh, and when Au3 plus comes up, Au3 plus, 3 electrons, Au, okay, so uh, but this positive charge on the surface results in weight. So the metal surface is gonna have a partial or a temporary positive charge when it loses electrons to the cation in the solution, and that results in the positive charge seen across the surface of the metal, but from what I understood, the solution is also positively charged. How is the electric field formed? You're on right track. This part is subtle. Let's go. Metal loses electrons to Au3 plus. Some Au3 plus ions at the metal solution interface gain electrons and get reduced by Au atoms, which deposit onto the metal. Electrons are leaving the metal, so metal surface becomes slightly positive. Solution side. Most of the solution still has Au3 plus positive ions and counter ions. Right at interference, there's a layer of negative counter ions attracted to the newly positive metal surface. What? There's a layer of negative counter ions? Okay, negative counter ions attracted to the newly positive metal surface. This forms what's called an electrical double layer. The electric field formation. Electric field arises because of charge separation. Positive metal surface versus nearby layer of ions in the solution. Even though the bulk solution is positive, the local region near the metal has an excess of negative counter ions. By convention, the electric field. Okay. So we're considering this Au3 plus solution having counter ions. Is that always the case? So it points from slightly positive metal towards a negative layer of the solution. Why this matters? This field opposes the further electron transfer from the metal to solution. This field opposes further electron transfer from metal to the solution. Okay, it's the first. So this is. Okay, this is a new thing I have to add to my diagram, but I'm wondering, is this always the case? Like, there's always gonna be counter anions to form the layer, even if it's what the anion of the metal itself. Where is that F? I forgot the F. Mute. Guessing we reached the limit. Siri. Siri just pop up. Sh- the automation is not working as I wanted, but it's trying. It's trying. Again, wasting time. Electroneutrality must be maintained in the solution. Yes, almost always. Electroneutrality must be maintained in the solution. A solution can have a net charge in bulk. Even if the metal cation is, or any others, there's always counter ions from the salt that dissolves to make the solution. So for every positive ion, there's a negative ion somewhere balancing it in the solution. Near the electrode interface, where the metal loses electrons, it becomes partially positive. The nearby negative counterions are electrostatically attracted to the surface, forming the electrical double layer. This happens regardless of what the counter ion is. It could be Cl or any anion present, even if the anion is part of the metal complex. The principle of the metal complex as a whole might be negatively charged, but when Au3 plus ion gets reduced at the surface, the released electrons can create a positive spot for the metal, and any nearby negative charges part of the complex or free in the solution will line up to balance it locally. Bottom line, yes, there's always some negative counter charge near the electrode, forming the double layer because nature doesn't allow isolated positive charges to float in the solution. So, a new thing is Counter anions in the solution is attracted by the partial positive. What is happening? Wait. By the partial positive charge on the surface results in electrostatic interaction for negative ions. So okay, so okay, in my diagram now, due to the partial positive charge on the surface of the metal, due to E minus with the cations making the surface positive, which results in an electrostatic attraction to negative anions or counter ions in the solution, which forms polar nature on the surface of the metal. Now I know the electric field is from positive to negative, and come on, and so here also it's from the metal to the solution, more precise to the layer of negative anions surrounding the metal. And what is this exactly? What does this show? This show for the cell. At what point are we at when this happens for the cell? and what, and also let me know how is equilibrium reaches after this. I could show you what I drew. I could share this later. First, let me understand what it is. You're visualizing it correctly. Let's unpack this step by step. What is happening at the metal surface? When the electrons leave the metal and reduce some EU3 plus ions in the solution, the metal surface becomes partially positive. Okay, then nearby negative ions, counter ions, attracted, then form a layer of interface. This forms a polarized layer, electrical double layer. This polarized layer, electrical double layer. The nearby negative ions in the solutions are attracted and form a layer at this interface. This electric field here points from positive metal surface towards the negative counter ions, just like you said. What this shows about the cell, the separation of charge establishes a potential difference where the metal and the bulk, between the metal and the bulk solution. This is the origin of the standard electrode potential of this half cell. This is the origin where did I read that? Origin of the standard electron potential of this. The standard for this half cell. At this stage, no external wire is needed. It's just the intrinsic potential at the interface caused by the charge separation. What does what point of the cell this represents? This is essentially the open circuit condition of the half cell. Electrons have partially moved to reduce cations, but the flow stops because electrostatic repulsion from positive metal surface opposes further electron transfer. The double layer form. Wait. Stop reading without context. No external wires needed. It's an intrinsic potential at the interface caused by the charge separation. Okay. The separation of charge establishes potential differences. The other what point of the cell this represents? Essentially the open circuit condition of the half cell. Electrons have partially moved to reduce cations, but the flow stops because the electrostatic repulsion from the positive metal surface the flow stops because the electrostatic repulsion from the positive metal surface opposes the electron flow. The double layer forms and prevents unlimited flow of electrons. Electrons flow. Wait. Electrons have partially moved to reduce cations. but the flow stops because the electrostatic repulsion from the positive metal surface opposes further electron transfer. Mhm. How equilibrium is reached. Equilibrium is reached when driving force of transfer electron decreases. A tendency of A3 plus ion to gain the tendency of the Au3 plus ions to gain electron is counteracted by positive charge. Electrostatic force between but but if counter ions form at the near the surface, the Au3 plus should also be coming up, or am I stupid? Even if they came in, okay. Uh-huh. So here, uh, this electrical double layer at some point it's gonna be at its maximum when uh, when the metal surface is showing positive, but when the layer of counter ions form, I'm guessing the Au3 plus is gonna again get attracted to this counter ion layer. How is that gonna turn out? Initially, electrons leave the metal, attracted to form a layer near the metal surface. This is the first part of the electrical double layer interaction with Au3 plus Au3 plus ions in the solutions are still positively charged. They're repelled by now partially positive metal surface, so they don't directly jump back to the metal. Instead, they stay in the bulk solution near the diffuse part of the double layer, where the net electrostatic field is weaker. Equilibrium balance. The system reaches equilibrium where chemical driving force, electrostatic repulsion from the positive metal surface, attraction of counter ions. These forces balance each other, so the Au3 plus ions don't keep moving towards the metal in bulk. Only very thin layer near the interface may feel the attraction. Ah. What happens overall? Some Au3 ion gets reduced and deposited at the metal surface plus counter ion layers form a stable double layer, giving a measurable potential difference. Au3 pulse in bulk solution stays in the solution, ready to respond if cell potential changes. Example, when you connect a wire. Okay. Now connecting a wire, that's gonna be different. Counter anions, cations, metal. Mm-hmm. Mm-hmm. Au3 plus. Positive. Electrical double layer. Electrical double layer, okay. Um, a bit curious on the counter ions forming at the surface of the metal. Is representing something related to the amount of positive charges in the metal, or electrons in the metal. I don't know, it feels like there are some relations between the counter ions forming and the E minus in the internal lattice. It feels like stupid. Yes, your intuition is correct. The counter ion layer is directly related to how many electrons have left in the metal surface. Example, the partial positive charge that develops electrons leaving the metal, counter ions forming to balance the surface connections to the metal lattice. The metal doesn't lose electrons from bulk, only from the surface layer interacting the solution. The lattice itself remains electrically neutral overall. The counter ions doesn't change the metal, but neutralizes the surface charge locally, forming the electrical double layer. I'll be right back. Huh. More electron transfer, larger positive surface, more counter ions. What is. Oh no, the headphone. Okay, okay. Shit. Oh. Gonna close the window, so. So I'm guessing I kind of understood. Okay, let's end this with what's gonna happen with the wire connecting. How is that gonna change the whole picture? Perfect. This ties everything together. When you connect a wire from the metal electrode to another metal or some same solution, you allow electrons to flow through the wire. Here's how it changes the picture. Before the wire metal surface loses some electrons to reduce gold, loses some electrons to partial. The counter ions in the solution are attached. Electrical double layer forms. Electron flow stops quickly because electrostatic repulsion from the positive metal surface balances the reduction tendency. System is in equilibrium after connecting the wire. The wire provides path for electrons to move freely. Electrons can flow from metal to another electrode depending on the surface charge of the metal just as electrons move, because now metal can lose or gain electrons without building up a huge positive or negative layer. Electron flows. So when electron flows, how is that resulting? Hmm, I'm still a bit confused. Energy generation, flow, electron flow through a wire, current can do work. The potential difference between two electrodes drives their current continuously. Until equilibrium is reestablished. Concentrations are equalized, no net driving force. If the circuit is closed indefinitely with a redox active solution, reaction keeps on happening. Key point: the wire removes the restriction imposed by the metal surface charge. Electrons no longer stop because of the local positive buildup. The electrical double layer still exists, but it continuously adjusts as electrons flow. Okay, let me understand this. Let's say I connected the wire to and same electrode to another AU metal in the same solution, and that was just dunked in same solution. So what is gonna happen? Now the system is basically two identical half cell connected. Initial step: the first AU electrode has partial positive charge. because some electrons were lost to reduce. The second is fresh, no charge separation. The electron movement through the wire. The wire allows electrons to flow freely between the two metals. Which way the electron flow? Initially, very tiny difference in potential due to surface charge. Electrons from electrode with higher Fermi level, more negative potential. More negative potential, what does that mean? To one with the lower Fermi level. This movement neutralizes surface charges at the first electrode and starts building a slight charge on the second. As electrons leave the first metal, the Au ions near it are more likely to accept electrons and deposit as Au metal. The second Au electron now receives electrons. Some could also reduce, but the driving force is smaller because both electrons are identical and in the same solution. The counter ions in the solution constantly adjust to local surface charge. They cluster near positive regions and spread out where electrons equilibrium. Eventually, because both metals are identical and in the same solution, there is no net positive difference between them. Connecting a wire between two identical metals in the same solution initially allows very small adjustments, but overall no sustained current occurs. If you want continuous electron flow, the electrodes must be in solution with different redox potential, example, two different cations. So in your metal diagram, electron flow starts briefly, counter ions move slightly, eventually the system settles. Fermi, Fermi, so could you explain more on this? Because one electrode is having a positive charged surface due to what? Due to what? Solution. And when a new electrode is connected by a wire, the electron flow is from the new one to the old positive one, so it can or is it the flow of electrons is from the partial positive electrode to the new one, so the old one forms more positive surface due to less electrons, and the new one has more E minus to share, thus the uh, cations, anions, start moving towards the new one, and at some point both will be having an equal form of positive surface charge of surface, thus equilibrium. Let's carefully untangle this. Think step by step at this electron level and surface level charge. Initial charges, old electrode already in the solution. Some electrodes move from the new electrode to the old electrode. Counter ions in the solution shift towards whichever electrode is more positive. Initially, they cluster more on near the old electrode because it has positive surface. As electron flow continues, the charge differences increases. Counter ions redistribute, moving towards the newer electrode. Eventually, electron flow stops when the Fermi level equalizes. Electron flow doesn't make the old electron more positive. It reduces the negative charge. It reduces its negative positive charge. So if this happens, then the new electrode will be having less Au3 plus anion to Au deposited on the surface, compare to the old one, as new one loses electrons right when it's connected with wire to the old one, and the new one the new as new one loses electrons right when it's connected to the wire, and the old one The new one is already losing electrons, so the counter starts less A3 plus. Ah, come on. Exactly, that's the right way to think about it. Old electron, new electron neutral. Old electrode loses positive surface charge partially as a gated electrons. New electrode slightly positive, starting to attract counter ions. Impact on A reduction, metal deposition. Hmm. A reduction will proceed, but now the rate depends on local electron availability and surface potential. Uh-huh. So so it's not it's not gonna balance the amount joined even though they are of same size, just that one was there a bit early than the next one. Or in long term, they are gonna be equally distributing the AU AU3 plus conversions and the counter ions surrounding the metal. Okay, they balance. I know people. These a lot of these stuff are just common sense, but when you are not that intelligent, when you're not there, you gotta. If you're me, I gotta look into this stuff, bro. Sometimes my brain can't come up with answers. I gotta just keep on searching. Well, I gotta cook something. I'm starting to feel hungry. I gotta load my laundry, and we will be back. Starting with electrode potential. Peace.